Next, we will look into a more complex example of CMOS gate based combinational circuit realization. So, let us consider the example where it is given by output is D plus B into A into B plus C, say this example. Now, what is said is that when you are doing it, so we should have a N network and a P network. So, N network consists of the N type transistors which constitutes the pull down network, and we have got this P type network which is corresponding to the pull up network. So, this is the pull up network. So, this part upper part is the pull up network, lower part is the pull down network. Now, how do we realize the circuit? Now, as a rule what we do is that in the from the expression we find out the sum of the parallel terms, like say in this expression if you look into. So, D is one term and this A plus A into B plus C is another term. So, these two terms are in parallel. So, in the N network we will have this D into D and this A into B plus C as two parallel branches. Like here you see that D is one branch and that A into B plus C is in parallel with that, and in the A into B plus C A and this dot is there. So, after A the remaining part B plus C will be in series with A. So, that is what is happening. So, A is there and after that this B plus C. So, that is in series with A, and B, since there is a plus between B and C. So, this B and C, these two transistors will be in parallel. So, given any logic expression, so you can directly draw the pull down network for every plus symbol. So, you can think that the corresponding portion of the circuits will be in parallel to each other, and whenever we have got the dot or AND, so those portions will be in series with each others. Now, once you have completed the pull down network, now you have to draw the pull up network, and for the pull up network, so it is just the complement of the pull down network. So, whatever is in series in pull down network will be in parallel in pull up network, and whatever is in parallel in the pull down network will be in series in pull up network. So, if you look into the example, so D is in parallel with this part in the pull down network. So, in the pull up network D will be in series with the remaining part. So, that is what is happening. Similarly, B and C are in parallel in the pull down network. So, in pull up network they are in series. Similarly, with this B and C, A is in series in the pull up network. So, in the pull down network I will have this A in parallel with this B and C portion. So, this way we can very easily draw the CMOS transistor level diagram of any combinational logic circuit or combinational logic function. So, what is required, of course, the output should be in complemented form. So, if output is not in a complemented form, so you can put another inverter after this to get the function. Now, to understand that, just to get the confidence that this circuit really realizes the function that we are looking for. For example, in this case if D is equal to 1, then the output will be equal to 0. So, let us see whether this happens or not. So, if D equal to 1, so this transistor is on, okay. So, irrespective of other transistors, and since D equal to 1, this transistor is off. So, this transistor is on and this transistor is off. As a result, we cannot have a current flow path from VDD to VDD, the supply voltage, to the output, whereas from output to ground there is a connection via this transistor. So, the output will become equal to 0. So, if D equal to 1, we will get a 0 here. For getting output equal to 1, what is required is this term should be equal to 0 and this whole term should be equal to 0, and for that purpose it is sufficient to put A equal to 0. So, if we put D equal to 0 and A equal to 0, output should be equal to 1. Now, you see, look into this circuit, if D equal to 0 and A equal to 0. So, this transistor is off and this transistor is also off, this transistor is also off. Now, naturally there is no current flow path from the output to the ground. So, that part is disconnected. Upper side, so this A is getting a 0. So, this transistor is on and D is 0. So, this transistor is also on. So, we have got a current flow path from VDD to the output. So, naturally you will get a high at the output point. So, this will give output equal to 1. So, in this way, using complex CMOS gates, so we can realize combinational functions very easily. So, next we will look into the properties of this complementary CMOS gates, why is it so popular. So, it has got high noise margin. We will explain this term in the next few slides. VOH. So, VOH means what is the output voltage level when we are which we are considering to be high. So, we have got VDD, that is the supply voltage which may be close to say 5 volt, and VSS or ground which is say be equal to 0 volt. Now, you may say that anything above 2.5 is considered as logic high, and anything below say 2.5 is a logic low. So, if we put a boundary like that, so this is 2.5 volt, above this is high and below this is low. So, the problem is that there may be noise coming into the signal lines. As a result, some low may be misinterpreted as high, or high may be misinterpreted as low. So, normally what we have is this VOH is the voltage level above which we will consider the output to be high, and VOL is the voltage level below which we will consider the output to be low. And in case of CMOS, this VOH is at VDD and VOL is at ground. So, they are at their maximum values. Okay. So, VOH can at most go up to VDD and VOL can be a minimum ground. So, both the things are satisfied. So, this has got a very high noise margin. So, we will explain noise margin in the next slide. There is no static power consumption. There is no static power consumption, as we have said that when these CMOS gates are in work, then there is never a current flowing path from VDD to ground. So, at any point of time either the pull up network is on, either the pull up network is off or the pull down network is off. So, it is never simultaneously both the networks are on. So, naturally there is never a current flow path from VDD to ground, okay, in the static condition. So, there is no static power consumption. So, CMOS consumes very less power. Comparable rise and fall time. So, rise time means that if you apply, if your input changes from say 0 to 1, how much time the output takes to rise from 0 to 1. So, that is the rise time. Similarly, fall time means when the input changes from say input makes a change and the output should go from 1 to 0. So, how much time it takes to go from 1 to 0. So, these times are pretty small in case of CMOS gates. So, that is why this is also one of the important feature, and highly compact structure. So, you can make in a less area less silicon area. So, you can put large number of CMOS gates that makes it area efficient. So, next we will be looking into some timing diagrams and hazards. So, these are the two important concepts that will be required for understanding the operation of these combinational circuits. So, as I was talking about noise margin, see suppose this is my total range. Okay. So, for any gate whatever be that technology, say in particular say CMOS. So, VASS, so VSS is generally equal to ground and VDD is the maximum supply voltage that we can have, okay, DC supply voltage that we have. So, VDD may be say equal to say 5 volt, or depending upon the technology. So, this voltage will be coming down. So, for example, if you are going to say 90 nanometer technology, then this will be around 1 volt, and so that way the VDD value will be coming down, and this is continually coming down. So, as technology is progressing, so VDD value is continually coming down. Now, my total range of voltage level that a gate output can have is from VSS to VDD. Okay. So, out of that to keep some margin in the operation of it. So, what we do? So, we mark these two voltages VL and VH. Okay. So, anything below VL is taken as logic 0 and anything above VH is taken as logic high. If a signal state is between VL and VH, so that is taken as an unknown level. The idea is very simple. It is because of the fact that due to noise. So, if suppose a signal line A is at logic 0, but due to some noise coming into it, so it increases slightly. Now, if it goes beyond VL, then it will be difficult to understand like what it is. Similarly, if something is VH, so if due to noise margin it decreases further. So, if it crosses this barrier and comes to this VL region, then it will be misinterpreted as a low. Okay. So, this barrier or this margin is kept so that noise cannot take a VH value down to VL or cannot take a VL value up to VH. Okay. So, that way it will help us in understanding the logic level. Sorry. So, consider this situation, like we have got two gates. Okay. So, both are inverters in this case, but it need not be inverter. So, output of one gate is feeding input of another gate. Now, when this gate outputs a high, okay, this gate outputs a high and that voltage level is VOH. Okay. This VOH should be sufficient to for the second gate to take it as high. So, if the second gate takes anything above VIH as high, so VOH must be above that. Similarly, if the second gate takes anything below VIL as low, this VOL value of the first gate should be lesser than that, otherwise there will be a misinterpretation. So, this is explained in the diagram here. So, say for the second gate, so this is the situation. So, it takes from ground to this voltage level as the logic low input range. So, that is the VIL. So, this much is the VIL for the. So, any signal coming between whose value is between 0 and VIL is taken as low by the second gate, and anything between this VDD and this VIH. So, this voltage level. So, anything between these two voltage level, that signal value is taken as logic high by the second gate. Now, what is the condition on the first gate? So, first gate, if it wants to make an output low, okay, so it should produce a value less than VIL. Similarly, if it wants to produce something high, it should produce a voltage level which is at least equal to which is more than this VIH value. So, to be on the safe side, so what we do for the output high and low levels of the first gate, so they are kept appropriately. So, this output low level is kept to be lesser than this input low level of the next gate, and this output high level of the first gate is kept as more than the input high level of the second gate. So, if there is a noise, suppose this first gate has outputted a 1, okay. So, first gate has outputted a 1 and the voltage value is voltage value is equal to VOH. Now, if there is a noise and that noise takes this value lower than say this, so it takes the value lower than this. So, in this region, in that case it will be the second gate will not be able to understand that it as a logic high. Similarly, if the first gate has outputted a low, so it has outputted this, and due to some noise, if it goes beyond this level, but the second gate will not be able to understand it as logic low. Fine. So, we have got this noise margin, which is the voltage difference between output of one gate and input of next. And so, in this case, so noise margin, this noise margin high is equal to VOH minus VIH. Similarly, noise margin low is VIL minus VOL. So, this way we can define this noise margins low and high, and this if this noise margin is high, that means will be more protected against the noisy environment. On the other hand, if some logic family has got this noise margin low, then there is a high chance of corruption in the operation of the circuit realized by in that logic family. So, noise must exceed the noise margin to make the second gate produce wrong output. So, that is the condition. Okay. Next, we will look into timing diagrams. So, timing diagram, this refers to the time response of the circuit. So, if you take the circuit over a period of time, and this input symbol, the input signals, like say in this case the function f equal to a plus b c. Suppose this a, b, c, they are changing their values in some form. Okay. So, in this diagram, so we have drawn the time instants, and these signals a, b, c, they are changing their values at different times. Then what happens to the output? Okay. So, here this f 1, f 2, f 3, f 4. So, these are corresponding to 4 different realizations of the function that we will see shortly. So, ideally whenever this a is equal to 1, the output should be 1. Okay. So, this, but you see that it in this one of the realizations. So, output is temporarily showing some 0. Okay. So, these are known as the hazards. Okay. So, there is a glitch in the output. So, output is otherwise 1, but at this point it is coming down. Similarly, at this point it is coming down. So, it can happen. How can it happen? So, that we will see in successive slides. Why does it happen is that the real gates, they have delays. So, if I have got an AND gate, then the AND gate had certain delay. So, as soon as this input, its input has inputs have changed. So, it cannot be the output changes immediately. So, it takes some time to change, and because of that the circuit may show some intermediate behavior which is not expected. So, say in this case what we have done, we have taken an input A and it is inverted by 3 stages, by 3 inverters producing outputs B, C and D, and finally they are ANDed. So, this A, so here B equal to A bar, C equal to A, D equal to A bar and A. So, we are supposed to get f equal to 0, but due to this delay of these inverters. So, it may so happen that you get some other behavior. How? See this A, suppose A is changing like this. So, A was initially low, and now it is changing to high at this point. It is being high this much, and then it is again going low. So, B, so if this inverter has got some delay, so this status change of A will be reflected at output B after some time. So, this is the delay of one inverter, if we assume like that. So, this much is the delay of one inverter. So, after that time your B will be going low. Similarly, at this point A is changing. So, after that inverter delay B will be high. Then the C output. So, this will again, this is a delayed version of delayed inverted version of B. So, this again shows the similar thing. So, as if B is delayed and inverted. Okay. So, we have got this symbol, this timing diagram. D is again another delayed version like this. Now, we are F is equal to D and A. So, D and A. So, in this part, the first part of the graph. So, A and D, A is low and D is high. So, we get a 0 at this point. After some time, so A has changed the value to 1 and D is 1. So, it is expected that my output should become equal to 1. So, it will happen after the delay of one AND gate. So, again this is taken as the gate delay. So, when A has become 1, so after some time D becomes F becomes equal to 1. So, this is reflected at this point after the delay, and then it remains high for this much of time, and then D became low at this point. So, after a gate delay, so this F has come down. So, so we were expecting to get a constant 0 at the output F, but what you see is a in between F has become 1. So, this is the this is called the hazard, okay, that we will see in more detail in successive slides. So, here this width of this pulse will be equal to 3 gate delays, and the delays they will cause a transient f equal to 1. Now, if we consider say f equal to a plus b c, that function, and we have got 4 different realizations of the function. In f 1 is a canonical sum of product realization, f 2 is the minimum sum of product. So, here this a is coming. So, from this a line, so a is connected to this OR gate, and B C they are ANDed, and that is fed to this OR gate. So, f 2 is the minimized sum of product, f 3 is the canonical product of some form, and f 4 is the minimized product of some. So, these are various realizations of the function f equal to a plus b c. Now, ideally we expect that for all the realization f 1 to f 4, they should have identical waveform, okay, because they are ultimately realizing the same function. So, we expect that they will give us the same waveform, but in reality it does not happen. So, so there are some glitches. So, if you look into this f1, f2, f3, f4, so there are some glitches in this f1, f2, f3, f4 there are some glitches, otherwise they are same, okay, otherwise all the waveforms are same. So, we will go to the topic called hazards and glitches. So, glitch is unwanted output. So, output should be say steady 1, in between it becomes a 0 for a very small amount of time, then again it goes to 1. So, a circuit that has got the potential to have potential for a glitch is said to have a hazard. Okay. So, it is ideal, it is expected that my circuit should be hazard free. Glitches will occur when different paths have different delays. Okay. To the output, if different paths have got different delays from the input, then the glitches may occur, and it causes circuit noise and dangerous if logic makes a decision while output is unstable. So, your say a combinational circuit has got a hazard. So, the output is not stable in between, and at that time if we take a decision based on the output of the circuit, so that is the incorrect. So, that creates a problem. So, that has to be. So, these glitches are to be avoided as far as practicable. So, how do we do it? So, we design hazard free circuits. Okay. So, this is one possibility, somehow we do modify the circuit so that it becomes hazard free. However, it is difficult when we are doing a multi-level realization. So, any combinational circuit, they can be realized in two form, one is called 2 level, another is called multi-level. In 2 level realization, we have got only 2 level, one AND level and one OR level, or one OR level and one AND level, like that. So, I will whereas for multi-level circuits, like say if I have got a function f equal to a plus b into c plus d. Okay. So, this is nothing but the circuit a function a plus b c plus b d. Now, if I realize it like this, then what I do? I have got one AND gate which is b c, another AND gate which is b d, and then we have got an OR gate where we have got this line and A connected. So, this is F. So, this realization has got two levels. The first level consists of the AND gates, second level consists of the OR gate. Now, if we think about say this realization, then it can also be realized like this. So, first we do an OR of C and D. So, this is C or D. So, this is ANDed with B, and then it is finally ORed with A. So, this circuit has got 3 levels. Okay. So, if you go by level, so this circuit has got 3 levels, whereas the first circuit has got 2 levels. So, these are multi-level circuits. So, whatever we will discuss with respect to these hazard and glitches, so they are valid for 2 level circuits. For multi-level circuits, it is very difficult to have this hazard problem solved. Okay. So, another possibility is that we wait till the signal becomes stable. So, there are two types of hazard, one is known as static 1 hazard. Static 1 hazard means that output ideally should remain 1, but in between there is a glitch and it goes to logic 0 for some small amount of time. So, this is called static 1 hazard. Similarly, we can have a static 0 hazard. So, static 0 hazard means the output will remain output should ideally remain 0, but in between it goes to logic high and then again comes back to 0. So, this is the static 0 hazard, and there can be a dynamic hazard. So, dynamic hazard means the output should toggle, like it should go from 0 to 1, but what happens is that instead of going from 0 to 1 directly, it makes this type of toggles. It first goes to 0 to 1, then again comes down to 0 and then again goes to 1, or it is 1 to the circuit should go from 1 to 0, but in between it makes some toggles 1 to 0, then 0 to 1, then again 1 to 0. So, finally, it settles to 0, but it in between it shows some transitions. So, gate delays, so multiple transitions are created. So, this type of hazard, so they are known as dynamic hazards. So, static hazard, so it often occurs when a literal and its complement momentarily assume the same value. This can happen due to the gate delays, that a circuit, one literal and its complement, both of them are having the same value, and through different paths with different delays, and it causes the static output to glitch. Okay, so, we will take an example. Suppose this is a circuit which is realizing some multiplexer. So, here this function f is here the function f is equal to a s or b s bar. So, if s equal to 0, then this a will go to f, and if s equal to 1, then this b will be in this, then this b will be passing to f. Okay. So, if s, so the realization will be like this, that, so this is the situation, but because of this because of the presence of inverter, suppose A and B both are continually at ground, and S changes its state from low to high. Since A and B both are low, then even if S changes its value, output F should not change its status, okay, because the OR gates they should always produce 0, because A and B they are both at 0, and this S is selecting one of them. So, one of the OR gate output will be 0 always, that is expected. But what happens, you see, due to the delay of this NOT gate, so this S bar does not get the value immediately. Okay. So, it takes some delay, and after that S dash becomes 1. Now, for say this much for this range of time, what is happening is that for the upper OR gate we have got A is equal to 0 and S is equal to 1. So, this OR gate output is 1 in this region. So, in this region A is 0 and S is 1. So, as a result it outputs a 1, and the lower OR gate, so it has got B equal to 0 and sorry, not in this region. So, if you take say this region of operation. So, here A is 0 and S equal to 1. So, as a result output of this OR gate is 1, and for the lower OR gate B is 0 and S dash is also 1. So, here also you get a 1. So, this AND gate inputs are 1. So, after the gate delay of this AND gate, so you will get this signal will be going to high. After some time this S will be becoming equal to 0. So, this lower OR gate will become equal to 0, and then after that AND gate delay, so this will be coming down to 0. So, you see that ideally we should not have this glitch, but here in the due to the presence of this glitch is appearing. So, this is a static hazard. So, this is the static hazard that we have. So, on the A plus B C function, so there can be multiple hazards that can occur. So, we will see them for few cases.